Okay, so as usual, let's um, y is equal to z squared is equal to summation over I comma j h j I minus h. So let's write it as in this way: summation of I comma j, where j does not belong to I or I plus one. Hij haj plus sum over of I equals to 1 to 25. Hai hai plus sum over of hai hai. So the reason why I wrote it in this way is because the stream has it repeats elements. Right? Um, so if I and j, so when I, so essentially by saying that j is not equal to I or I plus one, it means that we're looking at two different numbers. So essentially it means that uh, AI is not equal to AJ. So this is the first case. Okay. So if AI is not equal to AJ, uh, then what is the expectation of this? So yeah, I mean it's similar to the last problem, right? Where or the first problem that we dealt. So
Actually
AJ,
zero.
yeah. So this is delta IJ, similar to what we discussed. So yeah, so you have 25 terms for which this is one, and again 25 terms for which this is one. Uh, so yeah, so you get 50 as the correct. Oh, yeah. Is
But
it? 1 second. Hmm. Oh, okay, okay, okay. It's just a counting error. Yeah. Ah, okay, okay. Yeah, yeah. So it's actually two times this thing. You can see why it's two times this thing, right? Because because when you are taking the sum over of this, uh, each of these numbers from 1 to 25 appear twice in this because the stream is repeated. And similarly also, so here you have AI plus one, and you would also have AI plus one AI. So it's twice of that. So yeah, 100 is the right answer. It's not 50. Is it clear?
Yes, sir.
Okay. Okay. Then shall we move on to some different kind of problems? Do you have any particular
Oh,
problems
sure,
in?
sir. Sure, sir.
Okay. Okay.
Can we also do the third one and finish it and then we go to the other problems?
Okay. Okay. So right. Okay. So we have a class of 30 boys and 40 girls, and we want to arrange them so that the girls stand before the boys in the line. Right. So the idea is that from all possible selections, uh,
Sir, actually, we are arranging 50 students.
yeah.
So probability of exhaustive number of cases is 50 factorial. Is it right,
Yeah.
sir? Denominator occupies 50 factorial. But
Yeah, but
girl
it,
has
it's
to,
not, but yeah, it is 50 factorial,
but
uh,
girls
but
has to
some of these
occupy
arrangements are
the,
identified, right? So for instance, uh, yeah, so the, yeah, I mean, the number of arrangements is 50 factorial only, uh, but let's
I
say
apply
you have
simple
this arrangement
probability.
where you have girl one, girl two, and then boys, and this arrangement girl two, girl one, then boys. These two are identified with each other.
That is the sample space, sir. That is, I'm telling 50 factorial.
Okay.
Totally, you have 30 boys and 20 girls. Permutation only, sir.
Uh-huh.
So 50 factorial. So, but
Okay.
girls has to occupy the front portion, but girls has to stand together. Okay,
Yeah.
so you consider girls as a single unit. So you can
Hmm.
arrange them in 20 factorial into 30 factorial ways. So it is, I got the correct answer, but I
Okay.
applied some other technique there. That's all.
Huh. Okay,
Its money
that's
answer
fine.
is 20 factorial into 30 factorial divided by 50 factorial.
Huh. Yeah. Yeah. So that is basically like 1 by 50 C20, right?
Yeah.
Huh. Yeah. Yeah. That's right.
I applied simple permutation concept.
Huh. Okay. Yeah. Yeah, that's fine.
Got it, sir. Thank you.
Okay. Okay. Fine.
Is my argument is correct only, sir?
Yeah, yeah.
Yeah, okay, thank you. I have taken in that sense. I got the answer also.
Yeah. Sure. Okay. Um, Okay, so let's take an example. Um, this is random walks on graphs. So you know what a graph is, of course, right? Now, random walk means that um, you can model it as a random process, a Markov process, uh, more precisely, where at each time instant t, so let's say you have, so let's write it down, model this as a Markov chain. At each t, uh, if you take two vertices x and y, so you have a graph G, which is V and E. V is the vertices, E is the edges. So if you take any x comma y, which belong to V, then the probability, or basically the transition probability from yeah, so the transition probability from x to y uh, is equal to 1 by degree of x. So essentially what you're doing is that, let's say you have a vertex x, and let's say you have uh, its neighbors. Let's say you call them y1, y2, y3. Now you pick a neighbor randomly the from all possible neighbors of x, and you move to that neighbor. Okay, so this is the transition probability. Now the question is, of course, you can model this as a Markov chain. Now the question is, will this Markov chain have a stationary distribution? So let me write it. Will it have a stationary distribution? So let's say uh, pi is the initial distribution. Then will it have a stationary distribution? Always. In other words, what this means is, if I take this, so if I do p to the power n times pi, if I take a limit and tend into infinity, then will this limit always exist? Yeah, what do you think?
Sir, what happened to the value if X is a pendant vertex?
No, so this is a Markov process, right? So let's say at time instant t, you are at this vertex X, then you choose any of its neighbors randomly, and in the next time step, you move to that neighbor, right? And this is your transition map. This is the probability. Now, will it have a stationary distribution?
So there is no vertex which is of degree 0.
Yeah, so if there's a degree 0, okay, then okay. Let's assume that there are no degree 0 vertices.
Okay.
Assume connected graph, which means all vertices have degree greater than 0. Okay, so let us recall the criteria for stationary for a Markov process, for a Markov chain to be stationary. So the Markov chain has to be, number one, it has to be irreducible. And number two is it has to be aperiodic. So aperiodic means that what this aperiodic means is that probability of x comma x should always be greater than 1. Okay. Uh, so the important thing to note over here is that these are not necessary conditions. These are sufficient conditions. These conditions are sufficient enough to say when a Markov chain will necessarily have a stationary distribution. They're not necessary conditions. And irreducible means that uh, irreducible means that uh, there exists an R such that uh, this, so if you write the transition matrix as P, and if you take R of that R times P, then PR of X comma Y is greater than 0. Okay. Now the question is this irreducible? The answer is yes, it is irreducible, because if I assume that my graph is connected, then I can always move from, given any vertex X, I can always go from that vertex X to any other vertex in the graph. Not necessarily in the first time step, but in some of the later time steps, I'm able to move from that uh, from X to any other vertex because I have a connected graph. So this is an irreducible Markov chain. But is it aperiodic? The answer is no, it's not aperiodic, because uh, starting from this vertex X, you do not remain at this vertex X. You go to some of the neighboring vertices. Uh, in fact, it is periodic, and its period is 2, because let's say you go from X to this vertex Y, then from this vertex Y, you can again come back to X. So essentially, in 2 steps, you can be back to where you started from. Okay, so its period is 2. So it's actually aperiodic. So it's not aperiodic. And so it's the sufficient conditions are not actually met. So we can't actually say whether this graph will always have a stationary distribution. It's not possible to say that. Okay, but is it possible? So so when I say that it does not have it will not have a stationary distribution, it means that it will be irrespective of the choice of pi. Now the question is, can I find a choice of pi? So the question is, let's write it down. Does there exist there exists some choice of pi, call it pi 0, for which limit into the power infinity pi n v 0 exists. That is the question. In fact, we'll answer a simpler question. Does there exist a pi 0 for which p pi 0 is equal to pi 0? Okay, and the answer is yes. There exists a choice of pi 0 for which this is actually true. So what is that choice of pi 0? Okay. So what if we set pi 0 to be equal to uh, so pi 0 of x is set at degree of x. But you can't set pi 0 of x equal to just degree of x because it has to be a probability distribution. So in order to make it a probability distribution, you normalize it. So so for a graph, the sum over of degrees of each vertex is equal to twice the number of edges. Okay, this is a well-known fact. So you can set pi 0 of x to be equal to degree of x by twice the number of edges. Okay, so if that is the case, then what is p of pi 0? Okay, so if we do it for each vertex x, then it is equal to yeah. So then pi e 0 for any vertex y is equal to uh, sum over of probability of x to y, phi 0 of x. Correct. Now, now when is this term non-zero? So this term is non-zero only when so probability of x comma y. So here the summation is over x. So probability of x comma y is non-zero if and only if there exists an edge x comma y. Correct. So if there is an x edge to y, then you can move from x to y. Correct. So this summation is over x belonging to the neighbors of y. And what is the probability of x comma y? Well, the probability of x comma y is equal to 1 by degree of x. And what is pi 0 of x? Well, pi 0 of x is equal to degree of x by twice the number of edges. Okay. So this is equal to 1 by twice the number of edges, sum over of x belonging to neighbors of y 1. Now, what are the number of neighbors of y? The number of neighbors of y is equal to the degree of y. So this is equal to degree of y by twice the number of edges. So, and what is this? And this is equal to pi 0 of y. So we actually have p of pi 0 is equal to pi 0. So actually the distribution of this Markov chain is stationary from the first step itself. Is it clear?
Yes, sir.
Okay, great. It's clear, right? Now, let's take an example.
Will there be more problems, sir?
Yeah, I am seeing some problems. I don't know if you like them or not. So let's look at one problem. Um, so this problem is the random walk on groups. Are you familiar with groups? Are you familiar with the mathematical term groups?
No, sir.
Okay. Uh, okay, then leave it. So, okay. Okay, so then I think I'll stop here. Um, if there are no more questions. Um, let's stop here.
Sure, sir. I can mail you the recording of the meeting. I had recorded it from the
Yeah, yeah.
beginning.
If you have any further questions, you can send me an email. I'll
Sure,
send.
sure, sir. Thank you.
Okay, okay. Thank you. So this will be the last meeting that we have. Uh, your exams are on Saturday, I guess, which is 20th, right?
Yes, yes.
Okay. So all the best. I hope these sessions were useful.
Yeah, really, sir. Thank you very much. Thanks
Yeah.
a lot for taking this special session, sir. Thank you.
Yeah. Sure, sure.
Okay.
Thank you, sir. Thank you.
Thank
Okay.
you.
Okay. All the best. Bye.
Thank you. Thank you. Bye.